Welcome to section 8.5 of chapter 8, where we're going to be looking at partial fractions. This is a method that will help us integrate rational functions. Later in this chapter, we will see that finding the velocity of a skydiver and also finding the population of a species that is limited in size involves integrals with integrands that are rational functions. Similar integrals result from modeling mechanical and electrical networks. The goal of this section is to introduce the method of partial fractions for integrating rational functions. When combined with standard and trigonometric substitutions, section 8.4 that we just did, this method allows us, in principle, to integrate any rational function. The method of partial fractions is such that given a function such as f of x equals 1 over x minus 2 plus 2 over x plus 4, it is straightforward to find a common denominator and rewrite as f of x equals x plus 4 times 1 plus 2 times x minus 2 over x minus 2 times x plus 4, which reduces to 3x over x squared plus 2x minus 8. It's very easy to find a common denominator here, which is the product of both denominators. And remember that when you're making equivalent fractions for each, you have to multiply the numerator and denominator by the factor that's missing. So we're multiplying this first term, 1 over x minus 2, by the quantity of x plus 4 over x plus 4, and that gives us the first term in the numerator in the middle equation that we see. 2 over x plus 4 is missing the factor x minus 2, so we multiply numerator and denominator by x minus 2, which is actually a factor of 1, so we're not changing the value of this term, which gives us the second term in the numerator, 2, times x minus 2, the missing term, and then we can combine them into one fraction, which is kind of done here already, and then simplify. The purpose of partial fractions is actually to reverse this process. We want to go from something like 3x over x squared plus 2x minus 8 to these simpler fractions that we see in the top of the screen. Given a rational function that is difficult to integrate, the method of partial fractions produces an equivalent function that is much easier to integrate, and we'll get to see that. So what you see here is the problem we just looked at, but going in the opposite direction. We have a rational function that we take through this method of partial fractions, which then gives us a decomposition into partial fractions, multiple partial fractions. The original rational expression is difficult to integrate, where these two partial fractions are much easier to do so. So let's look at how this is done. Given a rational function, our goal is to rewrite it as partial fractions. We want to take the original rational expression, 3x over x squared plus 2x, and convert it into two partial fractions, a over x minus 2 plus b over x plus 4, which are the denominators are the factors of the original denominator, where a and b are constants to be determined. We started from the right side of the equation with the other way, so we already know what the answer is going to be, but I'm going to show you how to do this partial fraction decomposition, which is what this is called. Okay? So the first thing we're going to do is set the equations equal. We've got 3x over x squared plus 2x minus 8. When we factored the denominator, we could see that there were two factors, x minus 2 and x plus 4, which become the denominators on the right side of the equation. What we're going to do now is multiply both sides of the equation by the common denominator. So the denominator on the left side will disappear, and we're simply left with 3x. And both of these denominators will disappear as well, but the numerator will have the missing factor in it as well. Okay? So we get 3x equals a times x plus 4 plus b times x minus 2. if we simplify the right, combining like terms with x's, and then just remember a and b are constants, so combining terms that have no x's into just a constant, we get a plus b times x plus 4a minus 2b. Now on the left side of the equation, I added a constant of 0 here so that it's easier to see how these two relate and how this is really going to help us. So notice that in order for both sides of the equation to be equal, the coefficient in front of the x has to be the same. So in this case, a plus b has to equal 3. And our constant has to be the same. On the left side we have 0, on the right side we have 4a minus 2b, so 4a minus 2b has to equal 0 as well. So now we have two variables and two equations. This is a very simple process for solving in algebra. The first thing we can do is to solve the first equation for a, and we get a equals 3 minus b. If we then substitute that value, that expression for a, into the second equation, now we can simply solve this second equation for b by first distributing the 4 and then solving, and we get b equals 2. At this point, we can now plug this value back into the initial equation. A equals 3 minus b, or 3 minus 2 equals 1. And now we have our partial fraction decomposition because we know what the values of a and b are. A is equal to 1 and b is equal to 2, which we already knew, but again, I wanted you to see the process of how we get there. And this is a very simple integral to integrate, a very simple expression to integrate. So the steps that we just went through for partial fraction decomposition was to first factor the denominator, then do the partial fraction decomposition where you set each of the factors of the denominator as an individual term with those in the denominator and a variable a or b or c, etc. in the numerator. Then we clear the denominators, and then we solve for the coefficients using the system of equations to solve for each of the coefficients or the numerators. So let's look at our first example, integrating with partial fractions. This will actually have 3 different denominators. So if you want, go ahead and try this. We're going to do this following the 4 steps: factoring the denominator, partial fraction decomposition, clearing the denominator, and then solving for the coefficients. I suggest you hit pause and try this one and see if you can solve for the 3 numerators, the 3 coefficients, a, b, and c. Okay? The first thing that we have to do is to factor the denominator. If we factor out an x, because each term has an x, then we have x squared minus x minus 2, which that then factors is a quadratic that factors into x plus 1 and x minus 2. So we have our 3 factors, x, x plus 1, and x minus 2. The next thing we're going to do is to set up our partial fraction decomposition, setting a coefficient over each of the factors, a different coefficient over each of the factors from the denominator. And we can see here that we have 3 different coefficients, a, b, and c. The next thing we're going to do is to clear the denominators by multiplying both sides by the common denominator, x times x plus 1 times x minus 2. And in this we get a times x minus 1, x minus 2, plus bx times x minus 2, plus c times x plus 1. You can see that what you're multiplying each coefficient is by the other 2 denominators that are not present. For example, a, we multiply by x plus 1 and x minus 2. For b, we multiply by x and x minus 2. For c, we multiply by x and x plus 1. When we combine all these, multiply them out, FOIL them out, etc., and then combine like terms around the x variable, we get a plus b plus c, x squared, which is going to equal the factor or the coefficient of 3, plus negative a minus 2b plus c times x, which this coefficient, this expression, is going to equal the coefficient 7, and then minus 2a, it's the only one that doesn't have an x variable, is going to equal minus 2. So we can set these up, and the easiest one, of course, is to start with the constant at the end because there's no other variables there. So we can quickly solve for a, and that's our last step, is to solve for the coefficients. So we get that negative 2a equals negative 2, and of course that means that a equals 1. Then we can plug in the value of 1 for a in these other two equations. We get 1 plus b plus c equals 3, which reduces to b plus c equals 2. And then negative 1 minus 2b plus c equals 7. I think I said 7 there, it should have been 3, which reduces to negative 2b plus c equals 8. Now we have two equations and two variables. We can solve these. I'm not going to go through those steps. You can do that, and we get a equals 1, b equals negative 2, and c equals 4. And so what we're going to do now is integrate the right side of the equation in step 2 with those coefficients input. And integration is really straightforward now. We can see the partial fraction decomposition written on the right, and so these are all very simple. We get the natural log of x minus 2 times the natural log of x plus 1 plus 4 times the natural log of x minus 2 plus the constant of integration. And they've reduced this to one simple log using the properties of logarithms. Remember, everything positive is in the numerator, so we have the log of x times x minus 2. Everything negative is in the denominator, so that's x plus 1. And then, of course, any coefficient in front of a log using the power rule becomes the exponent on that argument. So we have x minus 2 to the 4th power and x plus 1 to the negative 2 power, or really to the square power, because we already used the negative, recognizing that it would be in the denominator. Okay? Now we're going to look at a shortcut for doing the partial fraction decomposition, specifically solving for the coefficients. Solving for more than 3 unknown coefficients in a partial fraction decomposition may be difficult. In the case of simple linear factors, a shortcut saves work. In example 1, step 3 led to the equation 3x squared plus 7x minus 2 equals a times the quantity of x plus 1 times the quantity of x minus 2 plus b times x times the quantity of x minus 2 plus c times x times the quantity of x plus 1. Because this equation holds for all values of x, it must hold for any particular value of x. By choosing values of x judiciously, it is easy to solve for a, b, and c. For example, if we set x equals 0 in this equation, this results in negative 2a equals negative 2, or a equals 1. Because notice that in the second and third terms, because you're multiplying by 0, b times 0 times another quantity, this equals 0, b equals 0, and c times 0 times x plus 1 also goes to 0. So we're only left with this first part of the equation on the right, and of course on the left, we're only left with negative 2 on the left. If we set x equals negative 1, notice the x plus 1 becomes 0, so the a term goes away, and the c term goes away, and then we can solve for the value on the left side, and we just simply get the b term. And so we get negative 6 equals 3b, or b equals negative 2. So can you think what we're going to use for the last value of x? Well, now that we have A, B, and C, we could just go back to the original and plug those in, but we can also do this as well. So what term is not in C, but that is in both A and B? Well, that's x minus 2. So if we set x equal to 2, notice these two variables or coefficients will disappear, and we'll end up with, again, setting x equals 2, we're going to get a different value on the left. We get 24 equals 6c, or c equals 4. In each case, we choose a value of x that eliminates all but one term on the right side of the equation. And notice what we did. We did that by setting each of the denominators in the partial fraction decomposition to 0 and using that value of x. So let's try example 2, where we're going to use the shortcut. Again, I highly encourage you to hit pause and try to do as much of this as you can before we start. And that's what these little paw prints are up here, is to always recommend that you hit the pause on the video and try whatever problems on the screen and try to get as far as you can based upon what we've already learned in this section. Okay? So we're going to follow the same steps, except this time, instead of factoring and using simultaneous equations or systems of equations, we're going to use the shortcut. So the first thing we want to do is factor the denominator, and this factors into x minus 1, and then the quadratic factors into 2x minus 1 and x plus 4. Then, of course, we rewrite the partial fraction decomposition as since we have three factors, we're going to have three coefficients, a over x plus 1, b over 2x minus 1, and c over x plus 4, where we add all of these. Our next step is to get rid of the denominator by multiplying both sides by the common denominator of all these factors. Of course, on the left, everything disappears, and then for each factor, whatever factor is not in the denominator is what is left there. So since x minus 1 is in the denominator of a, we're left with a times 2x minus 1 and x plus 4, the other pieces that are missing. For b, it's the other two factors besides 2x minus 1, as you can see here. And for c, it's the other two factors besides x plus 4. Okay? Now what we're going to do is to solve for the coefficients, and we're going to do this in a different way by setting x equal to something. In order to solve for a, we're going to set x equal to 1, what makes the denominator under the original a equals 0, because you can see that factor is not in the a term. But when x goes to 1, the b disappears because that becomes b times 0 times something else. And c also disappears because we get c times 0 times something else. And so when we set x equals to 1, the left hand of the equation becomes 9 times 1 squared is 9, plus 2 times 1 is 11, minus 1 is 10, equals 5a. 2 minus 1 is 1. 1 plus 4 is 5. 1 times 5 is 5. And so a equals 2. We can do this similarly with b, where the left side of the equation becomes 9/4. The right side, 1/2 minus 1 is negative 1/2. 1/2 plus 4 is 4.5, or 9/2. And negative 1/2 times 9/2 is negative 9/4 b. And so we can see here that b is going to equal negative 1 by solving that equation. And the last one, we're going to set x equals negative 4, again using the denominator. We set this one for x equals 1/2 because 2x minus 1 equals 0. Then we get 2x equals positive 1 and x equals 1 over 2, or 1/2. So for the last one, we set x equals negative 4 to solve for c, and we get 135 on the left, and we get 45 on the right, 45c, and that equals c equals 3. At this point, we can rewrite the integrand using the coefficients and solve, as you can see here. I'm not going to walk through all these steps. These are straightforward integrals. There are some multiples here. You'd have to do substitution. You'd have to set u equals 2x minus 1, then du equals 2 dx, and so you'd have to add 2 into the integrand and offset it by its reciprocal for the second one. So don't forget that this, I mean, they're pretty straightforward substitutions, but you need to do the steps. And I highly recommend that you work out all of these problems, not just read and move on to the next. Practice is what makes you master this course, and there are a lot of concepts and a lot of problems. So doing each problem that you come to in the lecture can be very helpful. So if you want to pause and read through this, this is taken directly out of your text. And you can see it in the textbook, but I would go ahead and try to do this and make sure that you can solve this as well. Notice here they did show you the substitution for the middle term. All the other ones are pretty straightforward because just du equals dx. All right. So this shortcut can really help as far as trying to find the coefficients, as we saw there, when they're linear denominator. Repeated linear factors. The preceding discussion relies on the assumption that the denominator of the rational function can be factored into simple linear factors of the form x minus a, where a is a constant. But what about denominators such as x squared times x minus 3, or x plus 2 squared times the quantity of x minus 4 to the third power, in which linear factors are raised to integer powers greater than 1. In these cases, we have repeated linear factors, and a modification to the previous shortcut procedure must be made. The modification is to include a partial fraction for each power of the factors beginning at 1, going up to the highest factor. So if we look at the example above here, notice that we have x plus 2 squared, so the highest power is 2 on this factor, and x minus 4 cubed, okay? Then the partial decomposition would look like this. Again, we start at, when there's an exponent on the linear factors, we start at a factor or an exponent of 1, and include all exponents up until the highest one given in the original factoring. So we have a over x plus 2 plus b over x plus 2 squared. Here we're at a cube, so we have plus c over x minus 4 plus d over x minus 4 squared plus e over x minus 4 cubed. So again, what we're doing is we're beginning with the linear factor as the first partial fraction, and then upping the exponent for another partial fraction until we get to the actual exponent on the factor. Okay? So this is how we have to modify the simplification process from before. And so you can see that it's getting a little complicated. So let's try example 3 now, where we try a problem with these repeated linear factors. Again, I highly recommend that you hit pause and try to get through as far of this as you can. And then if you get stuck, hit play and maybe keep hitting pause if you get stuck, and then you figure out what's going on and you can solve it on your own. The more you do on your own, the more questions of your own that you answer yourself, the greater is your learning, the greater is your retention. Okay, so we're going to follow the same steps as we did before. The first thing is to factor the denominator, and we can see if we factor out an x squared, which is in both terms, we get x squared times x minus 2. So here we have a linear factor that repeats itself because it has a power on it. Okay, so this means that when we're doing the partial fraction decomposition, we're going to include x and x squared. We start at an exponent of 1 and then go all the way up. And so here we have a over x plus b over x squared plus c over x minus 2, which only has a factor, or excuse me, an exponent of 1. We're going to get rid of the denominator, And what we get is 5x squared minus 3x plus 2 equals a plus c x squared plus negative 2a plus bx minus 2b. Now, we can see from above the first iteration of this where I just multiplied the coefficient times, again, the factors that aren't part of that. Notice here what we're multiplying by is x squared times x minus 2. So when you multiply a by that, one of the factors of x in x squared disappears, and that's why we get ax times x minus 2. This doesn't work exactly like the others when there's no exponents, because before you could just multiply the coefficient times the other denominators. But notice that part of a's denominator is in b. So you have to take that into consideration. So while it's easy when there's no exponent, just multiply the coefficient times the other denominators, it's a little more confusing, or have to be a little more careful when you have exponents on the denominators in the partial fraction decomposition. Okay, so when we clear the denominator, what we're doing is we're multiplying by the common denominator on both sides. So again, when you get a times x squared x minus 2 over x squared x minus 2, or excuse me, just a times this common denominator, notice again that one of the factors of x in x squared is going to cancel out, leaving you with just x times x minus 2. All right. So we could see here that in this first one, if we made x equals 0, then the c term is going to disappear, as well as the a term. And so you're just going to be left with b. So we could do that, set x equals 0, but then if we set x equals 2, a and b will disappear and we'll just have c, etc. So you could do that, but here it's quite straightforward. Since we have just negative 2b at the end, we can just set up the coefficients being equal to the mathematical expressions on the right. And I've done them color-coded. So 5 equals a plus c because 5 is on x squared and a plus c is on x squared. Negative 3 equals negative 2a plus b. They're both green because negative 3 and negative 2a plus b are the coefficients on x. And then, of course, negative 2b needs to equal positive 2 because these are the constants. So when we solve for these, we can start with b, and we can see that if negative 2b equals 2, then b equals negative 1. The middle term has b in it, so we can do that one next so that we can substitute the negative 1 in for b, and we get negative 2a minus 1 equals negative 3, or a equals 1 when we solve. And then finally, a plus c equals 5. If we sub in a equals 1, then of course c equals 4. When we plug in those values for the coefficients, then the integration is quite straightforward. Again, we get the integral of 1 over x minus 1 over x squared because b was negative 1, plus 4 over x minus 2 dx. This is, again, a very simple integration. I'm not going to go through these steps, and you can see the result here and check it against your own work. Hopefully, again, that you're doing these on your own and to get some practice in there. So we're about halfway through the lecture. This is a perfect time to take a break. Just get up and stretch. We've been at this a little over 20 minutes. We've looked at a lot of challenging concepts. So get up and stretch, go take a walk, go get a drink, take a coffee break, take a 15-minute break and come back and complete is what I would recommend. Of course, you're in charge, so do as you want, but giving your brain a little shower by taking a break can be a great learning strategy. Sometimes equations are going to be a little bit more complicated, and sometimes we're going to have factors, specifically quadratic factors, that cannot be reduced into simple linear factors with real numbers. For example, the polynomial x to the 9th plus 4x to the 8th plus 6x to the 7th plus 34x to the 6th plus 64x to the 5th minus 84x to the 4th minus 287x cubed minus 500x squared minus 354x minus 180 factors as the quantity of x minus 2 times the quantity of x plus 3 squared times the quantity of x squared minus 2x plus 10 times the quantity of x squared plus x plus 1 squared. So in here you can see that we have linear partial, so we have repeated linears, x plus 3 squared. We have a quadratic that cannot be reduced, x squared minus 2x plus 10. And then we have a repeated, because it's got an exponent on it, irreducible quadratic factor. So here we have quite a complicated partial fraction, if you will. In this factor form, we see linear factors, both simple and repeated, and irreducible quadratic factors that I'm labeling IQF, both simple, the first one without an exponent, and repeated when there's an exponent on there. With irreducible quadratic factors, two cases must be considered, just like we did before, both the simple and repeated factors. FYI, partial fractions of IQF, or irreducible quadratic factors, are of the form ax plus b over the quadratic equation. So it's not just a simple coefficient over the quadratic, it's actually a binomial here of a coefficient times x plus another coefficient or constant. So again, this is important to recognize that irreducible quadratic factors have a different numerator when we're solving them for partial fractions. So on our next example, example 4, setting up partial fractions, all we're going to do this time is just set up the partial fraction decomposition. You know, the a over x plus 2 plus b over x, whatever, okay? So we're only going to do the first two steps of partial fraction decomposition. So let's look at part A, sorry. So the first part is to factor the denominator. If we can see that there's an x squared in each of the terms, and that leaves us with x squared times x squared minus 4x minus 32. Well, 4 times 8 is 32, and so we can factor this into negative 8 and positive 4, and so we actually have the factors x squared, x minus 8, and x plus 4. There are no irreducible quadratic factors, but we do have a repeated linear factor in x squared. So we're actually going to have 4 variables. A over x plus b over x squared. Remember, we start at any factor that has an exponent on it, we start at exponent of 1 and go all the way up to that exponent. So we have a over x plus b over x squared plus c over the next factor, x minus 8, plus d over x plus 4. Okay, that's all we had to do for this, was just to set up the partial fraction decomposition. So now let's look at part B. The denominator is already factored. There are no factors of x squared plus 2x plus 2, which would factor the quadratic. So this is a irreducible quadratic function, x squared plus 2x plus 2. There are no real number factors for this. So we have a repeated linear function, and then we have a irreducible quadratic function. So we're going to have 4 variables again, 2 for the linear, x minus 2, and then x minus 2 squared, and then 2 for the quadratic, because remember, every quadratic has a form of ax plus b. So here we have a over x minus 2, b over x minus 2 squared, the repeated linear factor, and then the general form over the quadratic, which is cx plus d over x squared plus 2x plus 2. So hopefully that gives you kind of just a little practice and insight into these different forms. And now we're going to actually practice solving one of these irreducible quadratic functions. So let's look at example 5, quadratic factors, and taking an integral with some rational functions where there are quadratic factors in the denominator. Evaluate f of x equals the integral of 7x squared minus 13x plus 13 all over x minus 2 times the quantity of x squared minus 2x plus 3 dx. Again, we're going to go through those same 4 steps for partial fraction decomposition. The first is to factor the denominator. When we look at the quadratic equation, we're looking for factors of positive 3, which are either positive 1 and positive 3 or negative 1 and negative 3. And neither of those pairs will add up to negative 2. So we have an irreducible quadratic factor here. So this, you cannot factor this any further. The next step, of course, is to put it into partial fraction decomposition. Each of the factors is a denominator, so we have a over x minus 2, a linear factor, and then we have bx plus c over the quadratic factor. And remember, this is the form of partial fraction decomposition for quadratic factors, that there's 2 coefficients in the numerator, and it's of the form ax plus b, or any 2 coefficients. The third step is to get rid of the denominators by multiplying both sides by the factored common denominator. So we get 7x squared minus 13x plus 13 equals a times x squared minus 2x plus 3. Since there are no powers here, it's a times the other denominator, and then it's bx plus c times its other denominator. These are quite easy to clear out. If we go through, we can see we have an ax squared and a bx squared, so we get a plus bx squared. We have a negative 2ax. We have a negative 2bx and a positive cx. So we get negative 2a minus 2b plus c times x. And then as far as constants, we have a 3a and a negative 2c. As you can see here, I've color-coded these to hopefully make it easier. So the coefficient in front of x squared should be 7. So a plus b equals 7. The coefficient in front of x is negative 13. So negative 2a minus 2b plus c equals negative 13. And then the constant is 13. And so 3a minus 2c is equals 13. As you can see, these 3 equations, we have 3 variables, 3 equations. There's a number of ways you can solve these. You could set up a matrix if you wanted and do a reduced row epsilon form with your calculator. It wouldn't take long. That would give you a, b, and c. These are also not extremely hard to do arithmetically or algebraically. Okay? If you solve those 3 equations, I'm not going to go through that. Those are algebra skills that you should have. You would get a equals 5, b equals 2, and c equals 1, which rewrites the initial problem as a over x minus 2, so 5 over x minus 2 dx plus b is 2 and c is 1, so we get 2x plus 1 over x squared minus 2x plus 3 dx. So we're not quite done example 5 yet, but we have set up the integral to be a little bit simpler to solve. However, the second integral is not quite so easy to solve here. So notice, if we set u equal to the denominator, x squared minus 2x plus 3, then du would equal 2x minus 2. And if we had that in the numerator, this would work much better. So we can rewrite the numerator into which is 2x plus 1, which is the same as 2x minus 2 in parentheses plus 3. So by doing that, I'm now going to separate the second integral into two integrals as well, one with 2x minus 2 as the numerator and one as positive 3 as the numerator for the second integral. Okay, so this integral is still easy, pretty straightforward to solve. The second integral is not easy to solve. Well, it's not. We need to use some of the skills that we learned in a prior chapter. So let's look at the final pieces of this example. So we get the integral of 5 over x minus 2 dx. Very simple. This is 5 times the natural log of x minus 2. All right. The second integral, we have 2x minus 2 over x squared minus 2x plus 3. So this gives us, if we make u equal the denominator, this gives us du over u. So the integral is simply the natural log of the denominator, x squared minus 2x plus 3. Now this last one is still not easy to solve because we don't have, it's not factorable into linear factors. But what we can do is we can complete the square like we did in section 8.4. So if we complete the square, notice we get x minus 1 squared plus 2. Okay, this is of the form a squared, where a is the square root of 2, and x, instead of x, is going to be x minus 1. All right, and if you remember from the last chapter, if we have the integral of dx over a squared plus x squared, this equals 1 over a times the inverse tangent of x over a. And that's what we have here. Now, of course, there's a 3 on top instead of a dx, but we can pull that out in front. So that becomes a multiplier. So we get 3 times 1 is 3 over a, which was the square root of 2. Inverse tangent of x, but of course in this problem, x minus 1 is the u substitution for x. And then over a, which is square root of 2. So you can see all of those. They've just done a little bit of cleanup here using the combining the two logs, the power rule, sum rule, product rule, etc. Okay, and then they're explaining how they're explaining that last integral, which I just walked through those steps. Okay, so you can see these can be quite involved. This was a lot of steps. It actually even took me 2 PowerPoint slides, and I probably could have used more. So again, I cannot emphasize enough how important doing loads of problems is. You've got to practice these. You've got to practice these because it's not always readily apparent what we should be doing. And so we're so focused on now these quadratic factors and partial fraction decomposition that, you know, when I first, even as a teacher, when I first looked at this one, I was thinking, what am I going to do with that? Okay, so it's very, very important to be practicing these problems. So the preceding discussion of partial fraction decomposition assumes that the function is a proper rational function. Okay, if this is not the case, then we are faced with an improper rational function f. What we do is we divide the denominator into the numerator and then express the function in 2 parts. One part will be a polynomial and the other will be a proper rational function. So for example, if we look at f of x equals 2x cubed plus 11x squared plus 28 plus 33 divided by or over x squared minus 6, here we're going to perform long division by dividing the denominator into the numerator. Now this is old algebra stuff. It is a challenging algebra concept, but you should be familiar with this. Now remember, the way we do this is we focus on first term. So we go x squared times what gives me 2x cubed, and that would be 2x. Then we multiply through and subtract. Okay, so we're subtracting all of this. So 28x minus a negative 12x is plus 12x, which gives me 40x. 11x squared minus a negative is a plus 2x squared, gives me 13x squared, and 2x cubed minus 2x cubed gives me 0. I bring down the next term, and I look at the first term here. So I say x squared times what will give me 13x squared. Well, that's a positive 13, so I write plus 13. If it was negative, I'd write minus 13. I multiply through 13x squared minus 13x minus 78. Again, I subtract 33 minus a negative 78 is positive, is plus 78, which gives me 111. 40 minus a negative 13 is 40 plus 13, which gives me 53x plus 111. So this is our remainder. So the way that we express this rational expression in terms of a quotient and a remainder is that this is a whole number, much like if we did long division with numbers. We would say that, I don't know, 172 divided by 34 goes 5 times whatever number's up there, plus the remainder over what we're dividing by. And that's what we have here. So what's on top is kind of the equivalent of a whole number. So we have 2x plus 13. This is very simple to integrate. And then we have the remainder, 53x plus 111, all divided by x squared minus 6. And here we would do partial fraction decomposition or irreducible quadratic function, etc. of that nature. So finally, I want to go back and summarize the different partial fraction decompositions. We first looked at simple linear factors. This is where all the factors in the denominator were linear and there were no exponents on any of those. And so once we had factored our denominator into linear factors, we put a coefficient or unknown variable over each of those factors. And this is the first and the most simple partial fraction decomposition. So here we have two factors in the denominator. So this would equal a over x plus 1 plus b over x minus 2. And then we'd go through the rest of the steps. In some cases, we had what was called a repeated linear factor. And this is where there were exponents on the factors, the linear factors, once we had simplified it. And remember that when we have repeated factors, we have to include all exponents starting at 1 all the way up to this, the exponent that's actually in the denominator. So here we'd have a over x plus 1 plus b over x minus 2 to the 1 exponent, that's here, and then plus c over x minus 2 squared. If this was cubed, then we'd have another one here plus d over x minus 2 cubed. Then we learned about simple irreducible quadratics, and this was a different form for the partial fraction decomposition. So here we have a quadratic x squared plus 3x plus 1. We cannot simple it into real number linear factors, so this is irreducible. So our first term is ax plus b over this quadratic plus c over the linear factor there, x minus 2. C over x minus 2. And the last case we had was when we had a repeated irreducible quadratic. And this is when you had quadratic factors in the denominator that couldn't be reduced, that also had exponents on them. So we have a very similar problem as we had in step 3 there. And this one we just have a square on the quadratic. So notice again we're going to have two partial fractions, one with an exponent of 1 and one with the exponent of 2. Again, we start at 1 and then go all the way up to whatever that exponent is. So we get ax plus b over the first quadratic plus cx plus d over this the quadratic squared. And then we also have a linear factor here, so we'd have plus e over x minus 2. So this kind of gives you kind of a summary of all the different partial fractions we went through. There were a lot of other things that we covered in there and brought in from prior chapters.